Hello, and we're back to Physical Science section 14.3, the Earth as a Magnet. Hopefully you did those 14.2 questions already, and you're ready for 14.3, so let's begin with the Earth as a magnet, and as we begin we have to talk a little bit about how the Earth became known as a magnet. It all starts with this guy known as William Gilbert. William Gilbert is a great scientist and mathematician. He was a Christian as well. And William Gilbert published a book called De Magnete. I'm not sure I'm pronouncing that right, but it's Latin meaning of magnets. And it described the Earth's north and south magnetic poles. And we already kind of knew that the Earth was sort of magnetic. We didn't know how, but that's because lots of people were using, at that time, compasses, a navigational device consisting of a magnet free to swing so it points to the north. William Gilbert just described how a compass works. And there's a lot more to a compass than you might think. And we have to talk about this phenomenon called declination. You see, true north and magnetic north are not the same place. It sounds like a true-false question. And there's a slight difference in what is actually north. And the same thing goes with south and true south. So if you're talking about directly north, I mean straight northward, a compass will actually point you slightly at a different angle. And that's because the magnetic North Pole and the actual North Pole are different places. And now that doesn't mean a compass is unreliable. It's pretty close. But an isogonic line, as you can see in this diagram, will help you determine just how off your compass is. And so, as you can imagine, if you are right here at the in the U.S., your compass is going to point pretty well straight north. But if you are in maybe Africa over here, you can see how the magnetic line curves a little bit, making a slight declination moving towards the west. And so if you were following your compass at that point, you'd be going northwest. And the same thing for the South Pole. You can see that the South Pole isn't exactly all the way south. So that's a phenomenon known as declination. Inclination is kind of the opposite thing. And it has to do with the compass needle and how it dips downward towards the Earth. So whenever you hold a compass, right, hopefully you've held a compass before, it's kind of stuck where it is and can swing around to always point north. However, it can't really go up or down because of what it's fastened to. But if you were to take that needle out of the compass and just kind of hang it on a string, well, of course, gravity would pull it down. But let's say you're out from under the effects of gravity. It would still dip down at some points, or sometimes it would go completely horizontally. That's because of inclination and these isoclinic lines. Right here, along the magnetic equator, a magnet does not dip at all towards the Earth. However, if you were, I lost my pointer. If you're around here, let's say you're in Florida, and you got to think about the Earth being round at this point. If you are looking towards the northern, oh boy, there's people in the hallway. Temporarily disappeared because those people in the hallway really got my attention. Anyways, we were talking about if you were in North America. Now I'm going to use a trash ball to illustrate this. Here we got a trash ball. This is representing our Earth here. And let's say right here is the North Pole. And you're in North America, right here. Now, as you can imagine, you being in North America, the compass would point that way, because that's where the pole is. But it would also be angled slightly down. Why? That's because of inclination. And it's because the North Pole is actually sending its magnetic field in a way that pulls the compass point down into the Earth, because the quickest line to that magnetic pole is through the Earth itself. And that's a very unique phenomenon and has some pretty odd things that go along with it. So you can see how right here there's a very odd region of magnetism. And that's because the Earth's magnetic field is kind of everywhere, deflecting and doing all sorts of strange things. The dipping is caused essentially because of the Earth being round. And if you didn't understand the principle of inclination, that's okay. Just remember that inclination is where a compass needle dips, and it's caused by, or measured by, I should say, isoclinic lines. All right. The Earth is protected from solar wind, a stream of plasma from the sun. It's protected by the magnetosphere, so you can see here how the solar wind is coming at the Earth. The magnetosphere protects it, and the outer layer of the magnetosphere is called the magnetopause. It's the first thing that the solar wind hits. Some of the magnetosphere, well, I should say the magnetosphere doesn't block everything. Sometimes it gets trapped within what's called the Van Allen radiation belts. These solar charged particles remain there. And it's two belts right around here. If I can have my pointer back, thank you. Right around here and right around here where it's trapped, but there's nothing really there, so we don't have to worry about it too much. Sometimes they interfere with our satellites that we might have, but most of the time it really doesn't affect us at all. These charged particles from the sun are called ions, and you should remember from chemistry portion, I think chapter 7 or 8, that ions are charged particles. You have a cation and an anion, and these charged particles cannot hurt us because even if they get past the magnetosphere, the atmosphere itself destroys them, producing what we see in the northern and southern hemispheres of our Earth, the aurora borealis and the aurora australis, the northern lights, as we call them, or the southern lights, of course. And these are caused by those ions that get past the magnetosphere. The Earth is the only planet with an appropriate magnetic system. Many don't even have a field, so if you were to go to, let's say, Mars, I do not think it has a magnetic field. You would be pummeled with ions that would potentially destroy your skin and cause you some cancer very quickly. Or Jupiter has a magnetic field 20,000 times as large as the Earth. Well, as you can imagine, that magnetic field would be enough to really affect how we function. So much so that I believe that it would even cause some of the ion gates in our blood to be messed up and our heart to beat erratically, if at all. So that's kind of cool. God has made our Earth to protect us. And that is the end of 14.3. Make sure you do your section review 14.3 and include that in your packet. And we're done. So tomorrow is our video links for our labs. And Thursday is for studying for your test. Friday is your open book test. hopefully it won't be too hard for you. It is one of the shorter tests because there's not too much that happens in this chapter. All right, thank you, and I hope to see you again in our video segments sometime next week.